All right, well, thank you. Thank you very much for inviting me, and thank you very much for the introduction with all the details right. I'm not surprised for a second. And it's great to be here. It's my second time here at SIM, and I was telling a few people, last time I was here, we were working on something with Frederic and Kristina Vushkovic and Nicolas Trotnion, and our theorem kept falling down. So all I remember is working at night and sleeping during the day. And it's much better this time. So, so it's great to be here. And I'm talking about coloring graphs with forbidden induced subgraphs, though mostly it will be path. Oh, and I should say different results here. So this is a survey of what I've been doing for the last 7 years or so. So different results here, joined with different people, and of course I'll say it when we get to it. All right, so just a two-slide introduction that probably nobody needs. Coloring is hard. It's NP-complete to determine if a graph can be colored with k colors, even when k is fixed, when k is not part of the input. And this is kind of completely not related to anything else, but just for general impression, even to approximate coloring is hard. So if I give you a graph and I tell you it's 3-colorable, and I ask you to find the best coloring you can, the best known result at the moment is n to the 4/11. So it depends on the number of vertices of the graph. And it's NP-complete to approximate up to a constant. It's NP-complete to tell, to answer the question, is this graph not 3-colorable or yes, 1,000,000 colorable? That's NP-complete. So that's how hard it is. Okay. So now we're getting closer to what I'm actually thinking about, and that's attempting to make this problem easier by excluding some induced subgraphs, right? So if it's a very hard problem in general, maybe it gets easier if I promise you something and the graph is missing as an induced subgraph. And unfortunately, that doesn't help very much either because of a couple of results I'm going to show you now. So first of all, Kaminsky and Lozhin proved that it's NP-complete to k-color graphs of high girth. Even if I promise you that the input has high girth, the problem of k-coloring for k at least 3 remains NP-complete. And what does it tell you about trying to make the problem easier by excluding an induced subgraph? It tells you that if you exclude anything with a cycle, that doesn't help, right? Because if I exclude a graph on 100 vertices but it has a cycle, then graphs of girth 101 or at least 101 are still in my class, and I know it's hard to color them. So if I were to exclude something and hope for things to get better, I must exclude a forest. And then there's a theorem of Hollier that says edge coloring is NP-complete, right? And that means vertex coloring line graphs is NP-complete. And that means coloring claw-free graphs is NP-complete. And that means if I exclude something with a claw, that's not helpful because the class of claw-free graphs is still among the graphs I'm trying to color. So what we should include, so in order for the problem to become easier, I must exclude a forest and I must exclude something claw-free, right? So a forest that's claw-free. I'm talking about excluding just one graph, so I want all these properties to be in one graph. So there aren't very many claw-free forests. More specifically, the only things that you might hope to exclude and stop the problem from being NP-complete are graphs that are unions of paths. They're called linear forests, which means it's a graph where every component is a path. Just for notation, in this talk, PT is going to be a t-vertex path, right? With cycles, it's clear. It's clear what CT is. But PT sometimes has t edges and sometimes has t vertices, depending on whom you talk to or sometimes when you talk to them. So, so today, PT is a t-vertex path. Okay, so I'm going to summarize the state of our current knowledge. Right, so it's a matrix of infinitely many problems. You can decide with how many colors you're trying to color, and you can decide how long a path you're excluding. And so it's all here. So first of all, if you're excluding a path of length at most 5, then the problem is polynomial. So then, if you exclude, if you're trying to call, okay, let's call it this. So what about excluding path of length 6? 3 coloring is polynomial. 4 coloring is open, and I'll say something about this in a little bit. And then if you're trying to 5 color or more, that's NP complete. And if you think about it for a minute, you can complete this path, if this table. If you prove that something is NP complete, then everything toward the bottom and everything to the right is NP complete. And if you prove that something is polynomial, then everything up and everything to the left is polynomial. So somehow this is, I don't know if this is the minimal table I could have given you with all the information. And I should say, so, there are many theorems here, and many people prove them. And there's some color coding to say who proved what, or at least how I learned about the results. So the polynomial results in black and the NP complete results in red, they're all in this survey, and they're due to various people. Then the NP complete results in pink, they're newer, and they're due to Xinwei Huang. And then this guy with an asterisk, that's our theorem with Flavia Bonomo, my student Peter Macelli, Oliver Schaut, Maya Stein, and my student Ming-Shan Zhong, and I'll talk about that a little bit more. That's why it's with a star. It's sort of, right, there's what's known and there is a new result. And this is kind of a new result. This is a 3-year-old result. Okay, so let me continue explaining the table. So for t equals 6, everything, right, including a 6-vertex path, everything is known except for this open case. For t equals 7, everything is known. It's polynomial to 3 color, and it's NP complete from 4 coloring and on. And then if you exclude a path of length at least 8, 4 coloring and on is NP complete, but 3 coloring we don't know. So there are two things that are open. There is sort of one sporadic case here for 4 coloring P6 regraphed, and then there's a kind of infinite question here. Is there some length of a path where if I exclude it, 3 coloring is NP complete? Is it true that if I exclude P million, 3 coloring is NP complete? So I don't know, I don't actually really have a conjecture. I keep going back and forth on what I think about this. At the moment, I probably think it's NP complete, but I don't know. On the other hand, Xinwei, who killed all of these cases, has a proof that his method won't work for 3 coloring. So I don't know what it means, proof that the method won't work, but so that's an argument against it being polynomial, against it being NP complete. But anyway, that's just speculations. All right, so let me talk about open cases a little bit more. I already chatted about that. 3 coloring T at least 8. Now what about 4 coloring P6 regraphs? So people have been working on it. And there's sort of something interesting happening there. So first of all, the least version is NP complete, right? So you know what least coloring is. I'm going to define it later, but I'll tell you informally now, in secret. So you have a least for every vertex, and you want to find a proper coloring so that vertices must be colored from their list, right? If 1 is not in the list for this vertex, I can't color it 1. And so for every coloring problem, you can also ask, what about the least coloring problem? So in this case, the least version means every vertex has a list which is a subset of 1, 2, 3, 4. Can you color it? So sometimes it makes things easier, right? If all lists are 1, 2, then suddenly it's a nice, easy coloring problem. But in general, it's harder than general 4 coloring. And they proved that the least coloring problem was NP complete. Now, one reason to be interested in list coloring, and Pavel mentioned in his talk, is because if you're trying to design a coloring algorithm, one thing you can try and do is pre-color part of the graph and now ask, does this coloring extend? So one way to say it is to keep the part you pre-colored, but another way to say it is the fact that this is pre-colored turns the rest of the problem into a list coloring problem, because for every vertex, some colors are now forbidden. But this is not exactly the same as an honest list coloring problem, because you do have that little bit that define the list for you, and if you're interested in forbidding something, that's different. And so in their result, they proved okay. The point is, there's the list coloring version. There's also the pre-coloring extension problem, which means I pre-color part of the graph and now ask, can you extend it? So that we don't know. Their proof, their constructions that shows that least coloring is NP-complete does not work if it were a pre-coloring problem. So somehow it's very much on the cusp, very much on the edge. Pre-coloring extension problem is open. So there are some special cases where things are known. For example, if you also forbid C5, then it's polynomial, and that's a theorem with Peter Machelli, Juraj Stacho, and Ming-Xian Zhong. If it's triangle-free, that's also polynomial. That's a result of Zhou daughters, and I believe it's also known to have bounded clique-widths. That's your theorem, right? Thank you. And just a couple of months ago with Paul Seymour, our student Sophie Sperkel, and my student Ming-Xian Zhong, we were able to actually construct explicitly all triangle-free P6 graphs. So now it's really easy to color them. It's not a very complicated construction. It's not our structure theorem for closed-free graphs, but it will take some time to say it, and I'm not going to do it, but I'm just going to tell you that it exists. Okay, so, another thing I should say, the general problem, it's open, but it's probably polynomial. So Sophie Sperkel and Ming-Xian and I, we think we have an algorithm, a polynomial time algorithm, but it's hard and we're writing it up, and so I don't want to say it's solved, but I want to say it's with high probability polynomial. If I were to make a conjecture, I would conjecture it's polynomial. Okay, so that's what's known about the 4-coloring problem. Now let me go back to the 3-coloring problem. So this is the South American connection of this talk. So there were 2 groups that were working on this problem, as it turned out. We didn't know about that. There was my students, Peter and Ming-Xian, and myself. And then it turned out there was also Flavia and Maya Stein and Oliver Schaud, who is, for this purpose, an honorary South American. And so he's actually German. So with Peter and Ming-Xian, we had this long, difficult 2 papers that proved that P7, it's polynomial to color, to 3-color P7 free graphs. And basically we sort of proved everything we could about P7 free graphs, and we wrote it all down, and then in the end you could see that it's that now you can test it as 3-colorable. And then I got an email from Flavia saying, Maria, I noticed you're working on this, but by the way, we solved the triangle-free case, and it's 5 pages, and the complexity is, I don't know, n cubed, maybe n to the 7th, but something much, much better than what we had. And so somehow they managed to distill exactly the right properties. We kind of proved everything, and they managed to distill exactly the right properties and come up with a really nice, short, simple algorithm, but only for the triangle-free case. So then we figured we'll join forces and see if we can distill a little bit more. And turns out you can. So instead of it being 2 40-page papers, it's now 1 20-page paper. So that's a measurable improvement. And actually you can kind of explain it now. It's not just sort of everything I know in the world, but I can outline the proof, which is what I'm going to do now. Okay, so let's see. So first of all, let me tell you some tricks. So the first trick is, as I already mentioned, least coloring. Right. So again, here's the formal definition. Right. You have a least for every vertex, and a graph is colorable. So GL is colorable if there's a coloring, so that every vertex is colored from its least. Right. And coloring to me always means adjacent vertices get different colors. I omit the word proper because I'll only talk about proper colorings. So now the idea, kind of the very big idea, is to reduce the general coloring problem to a polynomial number of least coloring problems, but in such a way that, right, so with the property that if one of these least coloring problems has a solution, then the original problem has a solution, and if and only if. And, but the point is, the least coloring problems will somehow be easier. And I'll explain what it means easier, right? So the least coloring problems are such that I can solve them, while the original problem wasn't. So, right, well, okay, maybe I'll explain this in a minute. So here's a tool that explains why you could start with a problem, and there's some hope of producing least coloring problems that are easier. And that's a theorem of Edwards that says if I have a least coloring problem and I don't need to know anything about the graph, I have a least coloring problem and every vertex has least of size 2. Don't need to know anything about the graph, don't need to know anything about the lists. I just need to know that every vertex has least size 2. Then you can test if this least coloring problem is solvable. And it sounds kind of magical, but actually it's just 2 sets. You can, I don't know, maybe it doesn't sound magical to you, it sounds magical to me. But the reason it works is because you can do the same thing as you do with 2 set. Okay, so then you understand why there's some hope to that. Basically, we're trying to produce least coloring problems where lists have size 2. So, okay, now how are you going to do that? Well, there's a theorem of Campi and Schaut that's very useful here. And what they say is if you have a PT-free graph, then there's a subgraph in it that's dominating, meaning every other vertex has a neighbor in it. And it's simpler. So first of all, it's connected. And second of all, either it's just PT minus 2 or it's PT minus 2 free. So either you're somehow in a simpler case or it's just a small subgraph. So now, okay, so now let me illustrate how all this works. So let's first do the case. So we're going to, right, so I'm starting with a P7 free graph. And suppose first I'm in the, what will turn out to be the nicer case when I can find a dominating P5, right? The dominating PT minus 2, that's a dominating P5. And this step would actually work for general T. So I have a P5, or in general a PT minus 2, here it is. And then everybody else in the world has a neighbor in it. So what does it mean? It means I can try all possible colorings of this, of which there are only a bounded number, right? Because T is bounded. And then I can reduce the list of those, because everybody here will lose a color. Everybody here has a neighbor there. So that turns into a least coloring problem with all lists of size at most 2. So I produced, 3 to the T minus 2 least coloring problems, but I can solve them all. So, and obviously the graph is colorable if and only if one of those has a coloring. So that's what you do when the nice case happens, when you have a dominating path. So now let's think about the hard case, when what you have is just a simpler graph. So what we know, it's a connected PT minus 2 free graph. And here I'll be heavily using the fact that, T is 7. So there's a dominating graph H, which is P5 free, and it's dominating. So everybody else in there. So this is P5 free, and everybody else in the world has a neighbor in it. Now, P5 free is still too hard for me. I don't know what to do with it. So I'm going to use this theorem again. This has a dominating P3 or a dominating P3 free graph, and it's connected. Now, what's a P3 free graph? It's a union of cliques. And because it's connected, it's just a clique, but on the other hand, you want to check if your graph is 3 colorable, so you can assume there's no K4. So that means this bit H has a dominating P3 or clique of size at most 3. So that's good. So all I want is that there's a bounded size subset here called S, and S has bounded size. And now everybody in the world is distance at most 2 from S, right? People in H have neighbors in S, and those guys, maybe they're distance 1, maybe they're distance 2. So that's this picture. That's what the whole graph looks like. There's a bounded set S, and everybody else is distance at most 2. So now what you're going to do is pre-color S, and you're immediately in good shape for, okay, let me redraw this picture here. So here's S, it's bounded size. There are people called X, and they have neighbors in S, and then there are people called Y, and they have neighbors in X, and that's everybody. So for those guys, you're already in good shape because you've pre-colored this. So they lost the color, their list of size 2. Now you need to deal with Y. So there are a few steps to that. First of all, I want to arrange that Y is stable. Now, it's not actually true. It doesn't have to be stable. But I have a trick up my sleeve. I can pre-color a few more vertices and add them to S, and then this will, rearrange X and Y. I'm going to put in X everybody who's a neighbor in S, and then try and argue that what's left is stable. So let me explain how this works. So at the moment, there's 3 kinds of vertices in X. The types are defined by their list. So here everybody has list 1, 2. Here everybody has list 1, 3. Here everybody has list 2, 3. Now, suppose there's a big component of Y and somebody in X1, 2 is mixed on it. So that means there's somebody in X1, 2 that's mixed on an edge, right? Because this graph is connected. So let's guess somebody like that and pre-color, this and this and that. And now let's see how that makes the graph simpler. And I'm going to show you a nice case. So suppose I guess, I pass like that, I also guess a coloring. And let's say I got very lucky and the coloring I guessed is 1, 2, 1. So then I want to know, can somebody else in X1, 2 be mixed on an edge here? And the claim is no, because let's see. So suppose somebody else here is still mixed on an edge. Now, the fact that he's here means his list is still 1, 2. So that means he is not adjacent to anybody there, right? Because if he had a neighbor here, he started with 1, 2, he would have lost the color, his list would become size 1. What about those guys? The fact that they remain here after I've rearranged the graph means they're anti-complete to those 3 vertices. There are no edges between these 3 and those 2, because their lists still have size 3. So this pass and this pass, there are no edges between them. But that seed was connected, maybe I should have mentioned it, so I can get a pass between these 2 through this seed. And now that's too long. This goes 1, 2, 3, 4, 5, 6, 7. So that can't happen. So that's case 1.1 when I managed to guess this with those colors, but if you work harder and messier, it works. So that means that nobody, so after you do all that, you've arranged that nobody in X is mixed on a component of Y. So now what does that mean? Look at the component of Y. Maybe it's a singleton, which at the moment I'm happy about. Suppose it's not a singleton. So here's a component of Y and has some neighbors in X. So then you immediately see that this component must be bipartite. If it's not bipartite, I can see the graph is not colorable, right? So this graph is bipartite. And now look at the vertex here and look at its neighbors. It has, so this is bipartition. Look at the vertex here, look at its neighbors. So it has some neighbors here, and then it has some neighbors there. But the point is, these are completely joined to those. And that's a very good thing for you, because so if there's a vertex whose neighbors are complete bipartite, but actually even connected would work, then I know that in every coloring of my graph, this set must be monochromatic and this set must be monochromatic, right? If there's a 3 coloring and there's a bit like this in it, all of this must get the same color and all of those must get the same color. And then you get to reduce. You can delete this vertex and you can squish this to singletons, and you made your problems simpler. You need to check that after squishing those to singletons is allowed. That keeps the graph P7 free, but you can. And if you can't, there's another trick, but specifically here you can. Okay, so we are now in a situation where we enlarged S a little bit, still keeping it connected. But now Y is stable. So let me show you one more step, and that's going to be all the actual proofs I'll be doing. Okay, so now what are we going to do now? So here's x1, 2, x1, 3, x2, 3. So look at the vertex here. I want to know, I'm thinking about the coloring of this whole thing, and I want to know, can I have a vertex here so that there's a repeated color among its neighbors, meaning among its neighbors with different lists. Meaning, for example, it's a vertex here where it has a neighbor colored 1 here and a neighbor colored 1 there. So there could be, there's no reason why there shouldn't be. But if so, guess it. And by guess, I just mean go through all the vertices and all pairs of non-adjacent neighbors and try them. And you can do that, right? You branch into polynomial many instances, but you're allowed. So here's my guess. Now I claim after I guessed 1, it can't happen again. Because, so what happened? So I guess this vertex, its color, so it's colored 2 or 3 and 3 symmetric, and assume it's colored 2. Those 2 are colored 1. Now, again, I do the same thing. I rearrange the graph. Everybody who now has list of size 1, I put it in S. Everybody who now has list of size 2, I put it in X. So now, is it possible that, and I was given color choke that I'm not going to use. Now, is it possible that there is somebody else here who still has, can you see the blue? Or was that a bad move? No? Okay. I was given orange that I'm now going to use. So can I have a vertex here that still has the same property? 2 neighbors that could be colored 1. Well, so then look at this pass and at this pass, and let's try and understand what edges there could be between them. So certainly none of these are adjacent to those 2 because they would lose a color. And this is not adjacent to that because he would lose a color. And this is not adjacent to that because his list is currently 1, 2. So if he were adjacent to a 2, he would lose a color. So the only possible edge is here. And now, so there are 2 cases, maybe it's there, maybe it's not there. But the idea is, if it's not there, let's try and connect like that. So that's too long. Right, 1, 2, 3, 4, 5, 6, 7 if it's induced. So it's not induced, meaning those guys have neighbors here. But then if you think about it for 2 seconds, you get a pass like that instead, which is also too long. 1, 2, 3, 4, 5, 6, 7. So that's if the edge is not in, and if the edge is in, there's something else you do. So if this is an edge, then you go 1, 2, what do you do? 1, 2, 3, 4, 5, 6. And you need to argue a little bit to prove that you can go 5, 6 without getting chords, but you can. Okay, oh yeah, sorry. Every time I give this talk, I attempt to stop here. This seems like such a victory, but actually we're not done yet. Okay, so what did we prove? We proved that for every vertex here, there are no repeats. Right? I never get a 1 in this set and a 1 in that set. I never get a 2 in this set and a 2 in that set, and so on. So what does it mean? First of all, it means that you can't have a guy with neighbors in all 3 places, right? Because then he'll have neighbors in all 3 colors. So if you see somebody like that, you stop and say your graph's not colorable. So now if you look at somebody with neighbors in 2 places, you can argue that this set must be monochromatic and this set must be monochromatic. And that's something you can handle. Because remember, we're reducing it to basically a 2-set problem, right? The problem is list of size 2. Now, for free, you can throw in the constraint that some sets are monochromatic. So that's a little bit of sweeping under the rug, but it's true. That was actually a great contribution of Juraj Stacho when he came to Columbia, and we were working very hard. We were trying to squish the sets and prove that the graph remains P7 free, and it doesn't work. And then Juraj came and he said, but wait, there is this trick. Don't you know about this trick? And we said, no, but now we do. So you can delete this vertex and add the constraint that these sets are monochromatic. And now all you have left are vertices with neighbors in just 1 set. But then this is only a problem if it has 3 colors in its list. And then you can delete it, right? It doesn't change the coloring because all his neighbors are colored 1, 2. So now you've reduced it to a 2-set instance. Okay, so that's how that proof works. So now I'm done with the proof. Now I'm just going to chat for a little while. So okay, there is a related question that Paul Seymour asked. We proved that coloring P7 vertices is that 3 coloring P7 free graphs is polynomial. Now, there is a neat structural reason why that might be true, and that's because there are only finitely many abstractions, only finitely many minimal, non-3 colorable P7 free graphs. So that would immediately give you an algorithm to test 3 colorability. You just test is one of these graphs present. And, and maybe this is even true for all T, right? We don't know. So the answer is it's not true. Sorry. It's not true for all T. Alexei Petrovski constructed an example. Constructed an infinite family of minimal non-3 colorable graphs, all of which are P7 free. So there's no chance. But on the other hand, it is true if T is at most 6. So it is true that there are only finitely many 4 critical P6 free graphs. And that's a theorem with those guys. Charlotte is no longer South American, he's European now. So this is my collaboration with Europe. Jan's in Belgium and Mingshan is at Columbia. Okay, so let's keep going. And it turns out a more general version of Seymour's question was asked before by these authors. They said, for which H are there finitely many minimal finitely many H-free 4 critical graphs. So 4 critical means minimal non-3 colorable, right? It's 4 colorable and every subgraph is 3 colorable. And so the question is, for which H are there finitely many? Now there's some question, is it vertex critical or edge critical, but it's actually the same. There's finitely many of this if and only there's finitely many of those. So we're not going to dwell on that detail. And this is the question I actually want to talk about. So with the same set, with this set of authors, we answered it. We know the answer. So I'm going to tell you the answer. And that's the rest of my talk. So let me say H is powerful if there are finitely many, so if the answer is yes, if there are finitely many 4 critical H-free graphs. Now I want to know which H's are powerful. So okay, let's analyze what we already know. So first of all, if there's some graph and I know that excluding it keeps the problem NP complete, then I know this graph is not powerful, right? Because if the graph is powerful, that immediately gives me a polynomial time algorithm. So the claw is not powerful and the cycle is not powerful. So again, the only chance are those linear forests. So then we also have Petrovski's construction that tells you that P7 is not powerful, but actually if you look at his construction a little bit closer, you notice that it's, not only does it not have P7, it doesn't even have this. So this is not powerful, right? He has an infinite family of 4 critical graphs, none of which contains this. So that's not powerful. And so now here's our theorem. H is powerful if and only if it's a subgraph of one of these. So P6, or this, or that. So, and what this is, it's a 4H path plus a stable set, right? So this is actually infinitely many graphs. And I'll say something about the proof, but not nearly at this level of detail. So there's a closely related question, which, I don't know, it seems a little bit unnatural to me, but somehow Jan and Oliver think it's an important question, so we're going to make our paper twice as long and prove it. So what about the same question for least coloring? Is it true that there are only finitely many, or for which H's are there finitely many least coloring abstractions? And what's least coloring abstraction? That means it's a minimal graph, right? So it's a pair GL, which is not colorable, but if I delete any vertex and keep the same list, then it's colorable. Okay, so H is least powerful if there are finitely many H-free minimal abstractions to least 3 colorings. So least 3 colorings means lists are subsets of 1, 2, 3. And so we can figure that out too. And it's different. It's remember when I started, I said we know that 4 coloring P6 free graphs is NP complete, but we don't know what the answer is for pre-coloring extensions. It's the same kind of issue. Least powerful and not least powerful give you different answers, and I'll show you the connection to pre-coloring extensions in a minute. So the answer for this is that a graph is least powerful if and only if it's a subgraph of P6 or a subgraph of that, but not, right? It doesn't work if it's a subgraph of this, because there's an infinite family of graphs that don't contain this, and all of them are minimal list abstractions, and all lists have size 2. Okay, so that's the least coloring theorem, and I'll explain why there is a difference and what it has to do with pre-coloring extensions. Okay, so let me tell you something about the proofs. So first of all, if you think about it for not very long, though not 2 seconds, you'll notice that actually with everything I've said so far, it's enough to show that those graphs are powerful. Right, if I'm going for the non-least version, or it's enough to show that this and that are least powerful if I'm going for the least powerful version. Yeah, okay. So there are 2 halves to the proof. The first half is to show that and from now on I'll just talk about powerful just so that it's easier for me to speak, but actually everything I say applies to least powerful also, and when it doesn't I'll say it. So here's your minimal abstraction to 3 coloring. H3 minimal non 3 color. Then you're going to show that there's a subgraph sitting in it. So this is G. There's a subgraph sitting in it called H. And H has the property that there's a least assignment to H, so that this becomes a minimal least coloring abstraction. Minimal least coloring abstraction. And all these have size at most 2. So that's, okay, and so far this is not very hard. Take one vertex with an empty list. That so far satisfies everything I promised. But additionally, I want to say that H is not much smaller than the graph I started with. So there it says, so I'm sorry, in my slide I call it G prime, so I'm going to call it G prime here also. So there it says G prime is at most constant, the size of G is at most a constant times the size of G prime. That's a lie. What it should say is V of G is at most, V of G is at most, let's say 2 to the 2 to the V of G prime, just to be safe. I don't know that I actually need this much, but some function that you can calculate. Okay, so that's the first step. The first step is to prove that. If I have a big graph G and it's a minimal abstraction, then there is a smaller graph, but only slightly smaller, sitting inside it, so that there is a least assignment for it, so that that's a minimal least abstraction, and all leasts have size most 2. Okay, so that's step 1. Now, graphs with least of size at most 2 are nice, right? From Edwards' theorem, you know there's something special about them. So what you prove now is that anything like this is not very big. Anything like this is, has bounded size. And then you're done, right? Because you prove that a minimal least abstraction with least of size at most 2 has bounded size. And then you prove that, and you already know that your whole graph was not much bigger. So that's what you wanted. You prove that your whole graph has bounded size. And this is good. This works for the case when what you excluded as a P6, and it works for the case when what you excluded is this graph. And like I said, everything I said also works for least coloring abstractions. So this proof also works for least abstractions. Now, somewhere it needs to break, right? Because I better not prove by the same method that this is a least powerful graph, because it's not. So it turns out that this statement is false when you exclude that. Right? So if I just give you a collection of lists of size 2, it's not true that abstractions have bounded size. But I have a little more, right? Because when I'm thinking about this, I'm thinking about coloring. I'm not thinking about list coloring. So that means I know something about how I got this graph. I had some proof behind it that produced this graph for me. And what you know is that this is actually not just a graph with list of size 2, but that's a precoloring extension. The reason somebody here has list of size 2 is because it had a neighbor inside or outside, I don't care, but he has list 1, 2 because he had a neighbor colored 3. And that gives you extra power, and you can prove that if you knew that, then it has bounded size. Right? Because now it's not just free of those, but for example, I can't find in this graph something that looks like that, right? Because if in this graph I had this little picture, then he is 1, 2, so he somehow lost a 3. There's a 3 here. But this 3 cannot be adjacent to any of those because they didn't lose a 3. And that's my abstraction. So that's the difference. Okay, so now very quickly, how do you get all these statements? So first of all, let me do the first step. Okay. So the first step was trying to produce this graph with all lists of size 2. That's a minimalist abstraction. So what I'd like to say is pre-color something, and so let's see how to say here. So okay, so what you prove is, so again, here's your big H-free graph, and what you prove is that you can find a little subgraph called R, and you can pre-color it, and then you update from R, update meaning, right, if somebody has a neighbor in R, he loses a color. Now if you produce somebody new with list of size 1, his neighbors lose a color, and you update 3 times. You can't afford to update too many times. So you update 3 times, and then maybe you do a little more manipulation that I'm not going to describe. And then this has all list of size at most 2. Right? So now imagine you did this for all possible pre-colorings of R. So then what do you have? You have your R, and you have a thing like this for one pre-coloring, a thing like this for another pre-coloring, a thing like this for a third pre-coloring. Now, your graph was not colorable, so that means this contains a list abstraction, and all lists have size most 2, so we know it's not too big. So this contains a list abstraction that's not too big, and so does this, and so does that. And then you show, so here they are. There's one somehow sitting here, there's one somehow sitting there, there's one somehow sitting there. And then you show that basically the union of the list abstractions is the whole graph. Because suppose there's some vertex, far away from R that you could delete and not get any of those abstractions. Well, then with that vertex deleted, the graph is still not colorable. Right? These are all the abstractions you're getting from pre-coloring R, and you must contain at least one, and you must contain all of them. So, okay. So if you think about this for a minute, what you prove is that actually you can't lose anybody except maybe people in R. So then you show that your whole graph has size, the union of this abstraction, the sum of the size of these abstractions, which is not too big, because they're all bounded size, plus the size of R. So if you pre-colored was, if what you pre-colored was bounded size, that's great. That's still bounded. Now, unfortunately, we can't always do that. Sometimes you have to pre-color big things. But then you say, well, but then you're careful with what you pre-color. For example, let's say sometimes we pre-color a large complete bipetite graph. So is that what I mean? Let's say sometimes I pre-color one side of a large complete bipetite graph. So I've pre-colored something big. That's a little bit of a problem. But the thing is, so I prove that what's outside of it is small, is bounded size. And now I ask myself, how big can this be? Right? Given that the graph was minimal non-colorable. Because vertices here, they only have boundedly many types of neighbors outside. Right? There's only 1,000 vertices here, so there's only 2 to 1,000 types of vertices here. And inside they're all the same. So actually this was not that big. Right? If you had a lot of vertices here, 2 of them would have exactly the same neighbors and exactly the same list, but that wouldn't happen in a minimal abstraction. So you argue that if R is simple, you can still deal with it. Simple not in the sense that it has no parallel edges, but in the sense that it's not complicated. So now the only question is how you're going to find this R. And I'm not going to say much about that, but so sometimes it's easy. For example, if what you're excluding is if what you're excluding is this graph, and this is, I don't know, 100, then you can assume, so know this, we may assume there is that. And now this is dominating, right? Because if some vertex didn't have neighbors here, I would get that. So that's good. Now I pre-color this, I update once, and everybody lost the color. And this is bounded size. If you exclude P6, it's a little bit harder, and it's a lot harder, and it uses the theorem again that in a PT-free graph there is a bounded dominating PT-2 free graph, and or bounded size graph. And then if what you exclude is 2p3, that's really hard, and I'm not going to show you. Actually, I'm not going to show you anything, but this I really am not going to show you. So that's how you arrange for the thing that I unfortunately just erased. That, in your minimal abstraction, there's a big subgraph. There's an abstraction with all list of size at most 2, and it's not much smaller than the graph you started with. So now there is still the other half left, which is, what if I give you something where all lists have size at most 2? Right? Then I promised minimal abstractions there are bounded, but how are you going to prove that? So first of all, the honest answer is that the way we prove it is by computer. Jan and Oliver wrote a program that exhaustively generates all these things and finds that there are only finitely many of them. But there's actually, there's also a hand proof. It's just, it's too hard to write, I think, maybe, or too hard to make public. But I'm just going to tell you the idea because then we understand something. So, and for this case, we actually needed the hand proof. It's easier in this case than in general. So here's what you do. So here's a graph. There it is. And in it, I know it's not colorable, and I know every vertex has a list of size 2. So take a vertex. Let's say it has list 1, 2. Try coloring it 1. So then it has a neighbor that it's forced to be color 2. And let's say this neighbor had list 2, 3. So then I'm going to denote him by 2 sub 3. That means he was forced. I don't mean 2, 3. I mean 2, 1. So he was forced to be colored 2, but he had the option of being colored 1. This is the place where I started. Now let's say he has a neighbor called 2, 3, so then I'm forced to color him 3, and he has the option of, his second color was 2. And so you keep going like this, you get this forced pass, and if you colored everybody, then that wasn't an abstraction. So that means you got a contradiction, meaning eventually somehow you came back, he was 3, 1, but he's also 3 something, maybe 3, 2. Okay, so that happened. That's why you couldn't color this vertex 1. So now try coloring this vertex 2. And then it's the same thing again. You get this kind of, what we call it, propagation path, right? A parse of forcings, and at the end you get a contradiction. And this is the whole graph, right? This already shows you that you can't color this graph, and it was a minimal abstraction, so that's everything. So if I could show you that this propagation path cannot be too long, that's it. That's all I need to do. Now you start studying the structure of this propagation path. Well, obviously they're not induced paths because there's no long induced path in the graph. So they have chords. But on the other hand, you'd think if there's a chord, you can probably shortcut. Right? If there's a 2, 1 here and it's adjacent to somebody with at least 2, 3 here, well, why did you go all this way? You could have gone that way. So you think about it for a minute and you prove that, or actually more than for a minute, and you prove that there's only one type of chord. The only chord you can have is from a vertex of shape AB to a vertex of shape BC. Everything else you can shortcut. So somehow the chords are limited. You know a lot about them. On the other hand, there's a theorem that says, by Galvin, Sanders, and Sands, I think, that tells you that if you have a graph with no big clique and no long induced path, but you do have a long non-induced path in it, then it contains a large complete bipetect graph. So this path contain this non-induced path contain subgraphs complete bipetect graphs. Okay, so that tells me there's lots of chords, right? If you think of a path and you try to stick a complete bipetect graph in there, that requires lots of chords. So on one hand, chords are limited, on the other hand, there's lots of chords, and you try to play them against each other, and you produce the induced subgraphs you needed to produce. And I'm going to stop here. Thank you. Thank you.
Any questions? Comments?
I was wondering, could I have again that table that you gave with the...
Sure.
Because again, I don't know whether I missed something or not. I would like to understand
Sure.
This talk about the powerful. Yes, the powerful. Because you were saying something, as I understood. You say something. Once we know that the problem is NP-complete, we know that
It's not powerful.
Powerful because then you have you cannot have finitely many otherwise.
Right.
So it's a sort. Can you think that is a sort of an oracle to this? I mean, you. I thought I was shouting, but anyway. Were you listening to me?
Yeah, I could hear.
Okay. Okay.
You're facing me, but
yes,
you're with your back to everybody else, so it's easier for me.
Yes.
So an oracle meaning?
I mean, because if you know that the graph is powerful, you know that it cannot be NP-complete.
Right.
Right. Okay. So can you think that is another strategy to classify or to fill the entries of this table? I don't know.
Meaning, so what do you mean?
Maybe it's not.
An oracle
maybe
for
I'm
what?
not making sense.
I think I didn't understand you yet, but I.
Please help me. Yes.
So, but what do you mean? An oracle for what?
So you have this theorem that completely characterizes which
Powerful
graphs are the powerful ones.
Right.
So we know, because they are powerful, we know that the problem cannot be. Maybe I look at Bernard and he helps me with the question. So we know that for these graphs the problem cannot be NP-complete.
Correct.
So if we have this information, we can fill some entries of that table.
So you can make the same table by powerfulness, and now you're asking other still open slots. And
thank you so much for asking the right question. Yes, thank you.
Certainly. So, maybe the best answer is this table text takes into account everything I know about powerfulness. So, for example, here it says P7, three-coloring P7 free graphs is polynomial, but that's not done through powerfulness, because P7 is not powerful. It's a different algorithm. So in some sense, it's a little disappointing. Powerfulness is not all there is to making this polynomial.
Yes, that's what I mean by oracle.
Yeah.
That
yeah. So
know,
it's
but you don't have the algorithm.
Right.
In that sense.
That's right.
Thank you.
Sure. I mean, you can. This is about paths. You can also think about disconnected graphs, right? About forests, because the powerfulness theorem is about forests. And you can try and see what kind of table you can build about forests, because I don't have a table for forests. I only have a table for paths. Yes. But one could, and then sort of see what's left and see if you can fill it in.
Any other